Fellow mathematicians, we're going to take a look at the method of variation of parameters, which is likely the second method that you'll learn about to solve non-homogeneous ODEs. Now, for right now, ignore the theorem over here. Let's get right to the steps for how you use the method of variation of parameters. Now, it's actually really simple. We have our non-homogeneous ODE. Notice the coefficients here might be functions of x. You're usually going to encounter them where the coefficients are constants. The other important thing to point out, we want a 1 in front of the second derivative term. All right, so we have our non-homogeneous ODE. Step 1, we solve for the complementary solution, and we do that by solving the homogeneous ODE, the right-hand side equal to 0, and you can generally do that with constant coefficients very quickly. You'll get your solution here, the complementary solution, a linear combination of y1 and y2, which are going to be linearly independent. Now, once you have your complementary solution, the method of variation of parameters is very straightforward. You find a particular solution of this form. This is variation of parameters, where you have a combination of y1 and y2, but not with constants in front, or constant parameters, c1 and c2, but now u1 and u2 are functions of x. They are varying parameters. So basically, at this point, you have y1 and y2. You just need to figure out what u1 and u2 of x are. But fortunately, the theorem here for variation of parameters gives us two simple integral formulas that we just need to plug stuff into. So your ingredients to make use of these formulas for u1 and u2, which are factors in your particular solution, you need y1 and y2. You would have had that already. You're going to need to calculate the Wronskian. So you might have that set up as a 2x2 determinant. Make sure you're comfortable with that. And in addition to the Wronskian, you're going to need g of x, which is the non-zero right-hand side. So that should all be very easy to calculate. G of x you just identify, and then you plug them into these integral formulas, which sound really nice. You just plug stuff into formulas. The drawback, you have to evaluate those integrals, and evaluating integrals can be rather tricky. All right, so this method, the variation of parameters, is very short and to the point. Most of your work is going to be here in solving those integrals. If you're on top of all your integration methods, that should go very quick. Now, a lot of my students don't care about where these formulas come from, but a lot do. I teach about half engineering students, half science and math students, and the math students generally want to know where these come from. So I usually mention this briefly in class, but we're going to take a look at now a proof of where those formulas come from. So the basic theorem here, which you can use for your entire differential equations course, even when you get to non-constant coefficients, the basic theorem here says if you first have linearly independent solutions, y1 and y2, to this homogeneous ODE, how we find a particular solution to pretty much the same differential equation, just now a non-homogeneous ODE, is we have a solution of this form. This is your variation of parameters formula for the particular solution. The theorem says then u1 and u2 are determined by these integral formulas. Now, you don't have to know where those formulas come from or how to prove them to use this, but we're going to take a look at the proof right now. To get started with the proof of where the formulas for u1 and u2 of x come from, we need to understand two things. First, we're assuming y1 and y2 are solutions to the homogeneous ODE. And what that means is if we take individually y1 and y2, plug them into your differential equation, both y1 and y2 satisfy the differential equation, in which case this combination of y1, y2, and their derivatives both come out to 0. We're going to need that at some point in our proof. All right, what we're going to look for now is a particular solution to this non-homogeneous ODE. Notice it's the same left side, but now there's a non-homogeneous term on the right side, a function g of x. And what we look for are what u1 of x and u2 of x are that make this u1 times y1 plus u2 times y2, what makes that a solution to the non-homogeneous ODE. Now keep in mind, we're assuming we know what y1 and y2 are. We just have to figure out what u1 and u2 are. The end result will be those integral formulas that we had stated in the first part. All right, now we understand first here, u1 and u2 are functions of x, but just for calculations, let's just write it as u1 and u2, understanding that they're functions, just like y1 and y2. Now, how are we going to plug this in to the differential equation? We need to calculate derivatives. We need to calculate the first derivative and second derivative. So let's go ahead and do that. We'll calculate the first derivative. We're going to apply the product rule. So u1 prime times y1 plus u1 times y1 prime. And then we again apply the product rule to the second part, u2 times y2. So u2 prime times y2 plus u2 times y2 prime. And we need to think for a second before we go on. Now, we're trying to solve a second order ODE, and there's an immediate problem here. If we were to leave this as is and differentiate this again to get yp double prime, notice u1 prime will be differentiated to u1 double prime, and the same thing with u2 prime. That'll differentiate to u2 double prime. Now what's going to happen if we continue with that is we're going to replace one second order differential equation with two second order differential equations for u1 and u2. And that doesn't simplify it. So we're going to make a simplifying assumption here that prevents u1 prime and u2 prime from turning into u1 double prime and u2 double prime. Let me go ahead and rewrite this. I'm just going to switch the order of addition. Let me put u1 y1 prime first. And I'm going to put the other term, u2 y2 prime, in front. And I'm going to put the terms involving u1 and u2 and their derivatives at the end here. So just rearranging terms, u1 prime times y1, and then u2 prime times y2. All right, now again, our simplifying assumption is going to come from here. We don't want these terms present in yp prime, because if we were to differentiate these with the product rule, they're going to turn into u1 and u2 double prime, second order terms. So what we do is a simplifying assumption that those terms equal 0. Why? Well, it leads us to our solution, the formulas for u1 and u2 that we had stated at the beginning. Now, we're going to end up with a system of equations. This is one equation that I'll call the simplifying assumption. And that is going to simplify the work here and only give you first order differential equations for u1 and u2 rather than second order differential equations. So our simplifying assumption is that u1 prime times y1 plus u2 prime times y2 equals 0. All right, that's one equation for two unknowns. The unknowns here are u1 prime and u2 prime, which we can integrate to get u1 and u2 eventually. But for two unknowns, we're going to need a second equation. The second equation is going to be yp and all of its derivatives plugged back in to the non-homogeneous ODE. All right, now with our simplifying assumption, these terms get killed off. So yp prime, we're just going to write it as these first two terms. u1, y1 prime, plus u2 times y2 prime. All right, and again, our simplifying assumption kills off these terms, so we can just forget about them. Now, with this, we'll calculate the second derivative. And you can see here, u1 and u2, with the product rule, will differentiate to u1 and u2 prime. That's better than getting second derivatives, since we're trying to solve a second order differential equation right now. We don't want to solve additional second order differential equations. We want to do something to give us simpler differential equations, those of first order. All right, let's take our time. We're going to again apply the product rule twice. Basically, this is all the work. The rest of it is just plugging it all in. So let's get through the last derivative. Apply the product rule, u1 prime times y1 prime, and then add to that, differentiating the second function, u1 times y1 double prime. And if you're lazy, just change all your subscripts from 1 to 2. It works, but let's apply the product rule here. You'll get u2 prime times y2 prime. And then we add to that u2 times y2 double prime. All right, that is all of the work for calculating derivatives. The rest of it is we want to plug all this back into the non-homogeneous ODE. So before we move on, let's just have a little bit more room so that way we can plug all this in and then see where our second equation comes from. Now that we have the derivatives of yp prime and yp double prime, we just need to plug all three of them back into the non-homogeneous ODE. The hard work is done calculating those derivatives. We're just going to plug it in. And if you do replace all your y's with yp prime, and yp double prime, you get this mess of an equation. Now let's keep in mind where we are. We have two unknowns, u1 and u2, and we have one equation already, what we're calling the simplifying assumption. But for two unknowns, we need a second equation. And as it turns out, what we have here is our second equation, but it looks rather messy. Not much we can do with that. Now, this does simplify if we keep in mind that y1 and y2 are solutions to the homogeneous ODE. In other words, plug y1 and y2 in to that differential equation, and those derivatives will combine to give 0. Now, we're going to try to simplify this. There's not any terms that obviously cancel, but let's see if we can maybe factor things out from some of the terms. Now, we're going to notice that we have a u1 term here, another u1 term there, and another u1 term here. So instead of distributing everything and then factoring out u1, let's just factor u1 out from here. Factoring u1 out, we'll be left with y1 double prime. Factor u1 out from here, we'll be left with p of x times y1 prime. And factor u1 out from here, you'll be left with q of x times y1. And this might look familiar we are assuming y1 is a solution to the homogeneous ODE, and that is exactly the left side. And since it's a solution, that means we can replace this with 0, since y1 is a solution. So all this stuff in the brackets is 0 because we're assuming y1 is a solution to the homogeneous ODE. Now we might have an idea of what to look for the rest of this. Let's see if we can extract any U2 terms. And we have one here. So let's write that as we go. So we have U2. We'll be left over with Y2 double prime. Where's our next U2 term? Right here. We'll be left with P of X times Y2 prime. And we should have another U2 term here. We'll be left with Q of X times Y2. And since Y2 is a solution to the homogeneous ODE, this combination of Y2 and its derivatives also equals 0, because we are assuming Y2 is a solution to the homogeneous ODE. Now that's quite a lot of terms that we're just saying are 0, but it's not all of them. There are some that are left. So let's take a look at what's left. We really just have this U1 prime times Y1 prime. And the only other term that we haven't done anything with yet is right here, U2 prime times Y2 prime. And that should account for all the terms on the left. Most of them get grouped by factoring U1 and U2 out, and then the part in the brackets becomes 0, assuming Y1 and Y2 are solutions. This is what's left, the terms from the left side. That should equal G of X. And what we have here is a very simple, or at least much simpler looking than the original version here, second equation. What we get is that U1 prime times Y1 prime plus U2 prime times Y2 prime that equals G of X. And that, in conjunction with our simplifying assumption, these are our two equations for our two unknowns. We know how to solve that, a system of two equations for two unknowns, so let's get to that. From here, the work should be very straightforward. We have a system of two equations for two unknowns. We know how to solve that. We're going to choose to solve it by elimination. Now, your two equations, the first one is our simplifying assumption, and the second, that came from plugging yp and its derivatives back into the non-homogeneous ODE. All right? To solve this by elimination, let's decide to eliminate. Let's go first by eliminating U1 prime. This is really a system for U1 prime and U2 prime. So let's try to eliminate, by choice, one of the unknowns, U1 prime. All right, we're going to subtract these equations. In order to have the U1 prime term cancel out, we're going to need to have basically the same coefficients multiplying them. And notice we have Y1, but Y1 prime. Let's multiply each of the equations by the other Y1 or Y1 prime term. So for the first one, we're going to multiply that by Y1 prime. Second equation, we'll multiply that by Y1. All right, that's going to give us two new equations. And I'm going to take my time like I would in class. So let's multiply this whole first equation by y1 prime. So we should get u1 prime times y1 times y1 prime plus u2 prime times y1 prime times y2. And that equals 0. Multiplying by 0 still gives 0. All right, and our second equation, we're going to multiply that everywhere by y1. Again, take your time. So we get u1 prime times y1 times y1 prime plus u2 prime times y1 times y2 prime. Don't forget to multiply the right-hand side by y1 as well. And we'll be left with y1 times g of x. All right, now our two equations here, the u1 prime term should have the same coefficients. So we're going to subtract them. Let's subtract 2 minus 1. And we should find that the u1 prime terms cancel out, which they will. We're going to be left with only u2 prime terms. Since they each contain u2 prime, when we subtract, let's factor that out. So we'll get u2 prime times now y1 times y2 prime, but minus y1 prime times y2. All right, and subtract your right-hand side. Subtracting 0 doesn't do anything. We're left with y1 times g of x. It's a little odd that the integral formulas contain the Wronskian. Where does that come from? Well, that is exactly what's in the brackets here. That is the expression for the Wronskian of y1 and y2. So let's just rewrite that. Instead of the terms in the brackets, we'll rewrite that as the Wronskian of y1 and y2. We are almost done. Everything's falling into place. Our last step, to solve for u2 prime, divide by the Wronskian. So we get y1 times g of x divided by the Wronskian. We haven't solved for u2, but rather the derivative of u2. The main theme for a differential equations course, you undo derivatives by integrating. So here, solve for u2, integrate both sides. And what we get, our formula for the function u2 of x, is the integral of that right-hand side, the integral of y1 times g of x divided by the Wronskian. And that is the integral formula that we stated at the beginning of the video. Now we can see exactly where that comes from. Now, this is only half of your solutions here. You need to go through solving for u1 of x, and you can do that also with elimination. And if you go through similar work, you'll get the other formula, the formula for u1 of x. The work is a little bit different, but you'll get minus y2 times g of x divided by the Wronskian. And we'll leave it at that. Go ahead and go through elimination, and you should arrive at that for u1. All right, that completes the proof. That is where those integral formulas come from. For a differential equations course, you do not have to go through this proof every time. You should just be making use of those formulas, but keep in mind, those formulas might require you to evaluate some rather tricky integrals. Hopefully you enjoyed the video. Hopefully you enjoyed seeing where these come from. If you're liking the content, support the channel, like and subscribe.